Welcome to this comprehensive lecture on one of the most revolutionary experiments in quantum mechanics, the Davisson-Germer experiment that confirmed the wave nature of electrons. In 1927, Davisson and Lester Germer performed an experiment that would fundamentally change our understanding of matter, proving that electrons exhibit wave-like properties. To understand the significance of this experiment, we need to appreciate the revolutionary changes happening in physics during the 1920s. In 1924, French physicist Louis de Broglie made a bold proposal that would shake the foundations of classical physics. De Broglie suggested that all matter has a wavelength, given by Planck's constant h divided by momentum p, which equals h over mass times velocity. This meant that particles traditionally thought of as solid objects, like electrons, should exhibit wave properties under certain conditions. This concept of wave-particle duality suggested that matter could behave both as discrete particles and as continuous waves, depending on how we observe it. The question facing physicists was, is this just an elegant mathematical formalism, or does it represent genuine physical reality? This is where Davisson and Germer enter the story. Let's meet the two scientists whose careful experimental work would provide the crucial evidence. Clinton Joseph Davisson was an American physicist working at Bell Telephone Laboratories in New York. His colleague, Lester Germer, was a younger physicist who would work closely with Davisson on this groundbreaking research. Davisson, born in 1881, was the senior scientist, while Germer, born in 1896, brought fresh energy and experimental skill to their collaboration. Now let's examine the experimental apparatus they constructed to study electron scattering. The experimental setup began with an electron gun, which produced a controlled beam of electrons with specific kinetic energy. The electrons were accelerated through a known potential difference, then directed at a nickel crystal target with a detector positioned to measure scattered electrons at various angles. Crucially, the nickel target was not just any piece of metal, but a single crystal with atoms arranged in a highly regular, periodic lattice structure. A movable detector could be positioned at different scattering angles to measure the intensity of electrons deflected by the crystal. What did Davisson and Germer expect to observe based on classical physics? If electrons behaved purely as classical particles, like tiny billiard balls, the scattering should follow predictable particle mechanics. Classical particle scattering would produce a smooth, continuous distribution of scattered electrons in all directions, with intensity gradually decreasing at larger angles. Specifically, they expected to see a smooth, monotonically decreasing intensity as the scattering angle increased, with no special preferred directions. Classical Rutherford scattering predicts intensity proportional to 1 over sine to the 4th power of half the scattering angle. But what Davisson and Germer actually observed was completely unexpected and revolutionary. Instead of the expected smooth distribution, they observed sharp, intense peaks of electrons at very specific scattering angles. The graph of intensity versus scattering angle showed dramatic sharp peaks, with most angles showing very few electrons, but specific angles showing intense concentration. Remarkably, these peaks occurred at exactly the same angles as those observed in X-ray diffraction from crystals, a phenomenon known to be caused by wave interference. Such sharp, angle-specific intensity maxima cannot be explained by particle scattering, but are the hallmark signature of wave interference. To understand what Davisson and Germer observed, we need to understand Bragg's law of crystal diffraction. When waves encounter a regular periodic structure like a crystal lattice, waves scattered from different atomic planes can interfere constructively or destructively. Here we see incident waves striking parallel atomic planes in a crystal. The angle theta determines whether reflected waves interfere constructively or destructively. Bragg's law states that constructive interference occurs when n times wavelength equals 2 times the interatomic spacing d times sine of the scattering angle theta. Here n is an integer called the order of diffraction, representing how many extra wavelengths of path difference exist between waves from adjacent planes. The parameter d represents the perpendicular distance between parallel atomic planes in the crystal lattice. This equation precisely determines at which angles we should observe intensity peaks if the electrons are behaving as waves. Let's now calculate the de Broglie wavelength of the electrons in the actual experiment. In their key experiment, Davisson and Germer accelerated electrons through a potential difference of 54 volts. The kinetic energy gained by each electron is the electron charge times voltage, which equals 1.6 times 10 to the minus 19 coulombs times 54 volts, giving 8.64 times 10 to the minus 18 joules. This kinetic energy equals 1/2 m versus squared. Solving for velocity, we get versus equals square root of 2 ek over m, which gives approximately 4.36 times 10 to the 6 meters per second. This velocity is about 1.5% of the speed of light, so non-relativistic mechanics is appropriate. The momentum is mass times velocity, which equals 9.11 times 10 to the minus 31 kilograms times 4.36 times 10 to the 6 meters per second, giving 3.97 times 10 to the minus 24 kilogram meters per second. Finally, the de Broglie wavelength is Planck's constant divided by momentum, which equals 6.626 times 10 to the minus 34 divided by 3.97 times 10 to the minus 24, giving 1.67 angstroms. This wavelength of 1.67 angstroms is comparable to the typical spacing between atoms in crystalline solids, which is why diffraction effects are observable. Now let's verify that this wavelength correctly predicts the observed diffraction peaks. For the particular set of atomic planes in nickel that Davisson and Germer studied, the interplanar spacing is 0.91 angstroms. Using Bragg's law, n lambda equals 2d sine theta. For first-order diffraction where n equals 1, sine theta equals 1.67 divided by 1.82, which equals 0.918. Taking the inverse sine, we get theta equals 66.7 degrees. The intense peak in the measured data occurred at 50 degrees from the surface normal. Since scattering angle is measured from the incoming beam direction, this corresponds to a grazing angle of 40 degrees from the surface. When we carefully account for the scattering geometry and the specific crystal planes involved, the de Broglie wavelength prediction matches the observed peak position with remarkable accuracy. Let's pause and appreciate why this result was so revolutionary for physics. Let me ask you a question. What made this experiment one of the most important in 20th century physics? The answer is that it proved matter waves are not just abstract mathematical constructs, but represent genuine physical reality. In just 3 years, de Broglie's theoretical hypothesis was dramatically confirmed by direct experimental observation. Before this experiment, electrons were universally regarded as purely particle-like objects, with definite positions and trajectories. After this experiment, wave-particle duality became an experimentally established fact that had to be incorporated into any theory of matter. This experimental confirmation paved the way for the development and acceptance of modern quantum mechanics, including Schrödinger's wave equation. Interestingly, this groundbreaking discovery had an element of serendipity. Initially, Davisson and Germer were conducting routine studies of electron emission from metals and were not specifically searching for wave behavior. In 1925, a laboratory accident occurred that would change the course of physics history. A vacuum system failure allowed air to enter the apparatus, oxidizing the nickel target surface. To remove the oxide layer, they heated the nickel crystal to high temperature. This heating inadvertently caused the polycrystalline structure to reorganize into larger, well-ordered, single crystal regions. This accidental improvement in crystallinity made the diffraction patterns much sharper and more pronounced, leading to the clear observation of the wave interference peaks. This reminds us that sometimes the most important scientific discoveries come from unexpected places and require openness to surprising results. Davisson and Germer didn't stop with a single observation. They systematically studied how the diffraction pattern changed. They systematically varied the accelerating voltage, which changes the electron energy and therefore the de Broglie wavelength. Since wavelength is proportional to 1 over the square root of voltage, increasing voltage decreases wavelength. As they changed the voltage, the angular positions of the diffraction peaks shifted in exactly the way predicted by Bragg's law with changing wavelength. They also observed higher-order diffraction peaks, corresponding to n equals 2 and n equals 3 in Bragg's law. For second-order diffraction, 2 lambda equals 2d sine theta, giving different peak angles. Every single quantitative prediction of wave theory was confirmed with high precision, leaving no doubt about the wave nature of electrons. The similarity between electron diffraction and X-ray diffraction was particularly striking. X-ray diffraction from crystals had been discovered by Max von Laue in 1912 and was well established by the 1920s. Both X-rays and electrons, when scattered from the same crystal, produced identical diffraction patterns at the same angles. But here's the profound point. X-rays are electromagnetic waves, a well-understood form of radiation. Electrons were thought to be particles with mass and charge. Yet both produce identical diffraction patterns, proving that electrons must also have wave properties. For X-rays, wavelength equals hc over photon energy. For electrons, wavelength equals h over momentum. Different formulas, but same underlying wave principle. The wave nature of electrons has profound implications for atomic structure. Here's a fundamental question that puzzled classical physics. If electrons orbit the nucleus like planets orbit the sun, why don't they radiate energy and spiral into the nucleus? The answer comes from wave mechanics. Electrons and atoms exist as standing waves, not orbiting particles. In this representation, the electron exists as a standing wave pattern around the nucleus, with the wave fitting an integer number of wavelengths around the orbit. For a standing wave, the circumference must equal an integer number of wavelengths, 2 pi r equals n lambda, which equals nh over m versus. Rearranging, we get m versus r equals nh over 2 pi, which equals nh bar, the quantized angular momentum condition. This wave picture naturally explains the Bohr model's quantized energy levels and why atoms are stable. The Davisson-Germer experiment was a cornerstone in the foundation of quantum mechanics. In 1924, de Broglie proposed matter waves in his doctoral thesis, a radical idea that many found hard to accept. In 1926, Erwin Schrödinger developed his famous wave equation, describing how quantum wave functions evolve. In 1927, the Davisson-Germer experiment provided the crucial experimental proof that gave quantum mechanics its solid foundation. Theory, mathematics, and experiment came together to create the complete framework of quantum mechanics. In 1929, George Paget Thomson independently confirmed electron diffraction using thin metal films, approaching the problem from a completely different angle. In 1937, both Davisson and Thomson were awarded the Nobel Prize in Physics for their experimental demonstrations of electron diffraction. The wave nature of electrons discovered by Davisson and Germer has led to countless modern applications. Electron microscopy uses the short de Broglie wavelength of electrons to achieve resolution far exceeding that of light microscopes. Since resolution is proportional to wavelength, smaller wavelength means better resolution. Modern electron microscopes can image individual atoms and resolve structures at the atomic scale. Low-energy electron diffraction is used to study surface structures of materials, providing valuable information about the arrangement of atoms on surfaces and their interactions. This technique has become a powerful tool in materials, science, and nanotechnology, allowing researchers to study and manipulate materials at the atomic scale. In conclusion, the Davisson-Germer experiment marked a significant milestone in the development of quantum mechanics and our understanding of the wave-particle duality of electrons.